We're going to look at examples of exponential decay. So number 42, the penny lab. What about situations that do not grow? In this activity, you will explore a situation that behaves exponentially, but results get smaller. This is an example of exponential decay. We've talked about this previously. Follow the directions below in your to model exponential decay using pennies. Trial 0. Start with 100 pennies. Dump the pennies onto your workspace. Remove any pennies that have tails side up. Record the number of pennies that remain in a table where the input is the trial number and the output is the number of heads. Let's make that table quickly. We're going to start at trial 0. We have 100 pennies. Now, as I sit here, I can shake up my my cup of pennies, and I dump them all over the table. I'm going to remove all the pennies that had tails side up. Now that I've taken those out, I'm going to count how many pennies I still have that are the number of heads. Looks like I have 52 that are heads. So after one shake, I have 52 that are still heads. I pick up my heads up pennies again, I put them in my cup, I'm shaking them, and I dump them all over my workspace. I'm going to remove all the pennies that have tails again and count how many pennies remain with a heads. This time after the second dump or second trial, this time I only have 23 that are heads. I'm going to continue this process until all the pennies are removed. So in trial number 3, if I gather my pennies, shake them up and dump them all over the table, there are 17. Trial number 4, I gather them up, I shake and dump them all over. This time I have 10. Trial number 5, I gather them all up, shake, dump them out. This time the number that have heads is 4. Trial number 6, gather the heads, shake them up, dump them out. Only 1 has heads, and trial number 7 is 0. It was a tails, all the heads have been removed. Look at this pattern. Is there anything you notice? Is it what you expected to happen? And why did you expect that to happen? Now let's answer some questions about it. I'm going to take a moment to plot this graph so we can continue to answer the questions. Let's continue to answer the questions. Is this situation increasing or decreasing? Decreasing. What does this mean about the multiplier? Our multiplier needs to be smaller than 1. If it was 1 and larger, it would be increasing. Use what you know about the probability of flipping a coin. What would you expect or estimate the multiplier to be? Well, a coin, you have 50% chance of heads, 50% chance of tails, so I would expect my multiplier to be 0.50. Write an equation for the exponential function. So we'll write y equals, we started with 100, and we picked a multiplier of 50%, or 0.50 heads remain each time to the x. So y would be the number of heads remaining, and x would be the number of trials that have gone by. What output does your function give for an x of 0? So if x is 0, that means no trials have gone by. That would be the starting point, or starts with 100 pennies. Could there be an output value for -1? Not really in this word problem, but if we could, that would mean -1 being 1 trial previous. So I started with 100. If I went 1 trial previous to this, expecting 50% or half of them to be heads, we would have started with 200 pennies if there was a trial previous to when I started this experiment. Question F. In the context of this situation, what should the domain of the model that you wrote be? For the domain, well, when I look at this, I can't have a negative amount of trials realistically, so I would need my number of trials to be from 0 to infinity. And I'll write it like this. X could be 0 or go up until infinity. What family of functions that you saw previous in this chapters looks like the one you made? Of course, exponential. And we already wrote the equation above. Our last topic is something called half-life. Carbon-14 dating is used to approximate the age of ancient discoveries and to learn more about things like dinosaur fossils. Scientists have studied the rate of decay of carbon-14 and have learned that no matter how much of this element they start with, only half of it remains after about 5,730 years, which is called its half-life. Pretty much, half-life means however much you start with, how much time does it take so that you have exactly half of it left. All living things on this planet contain some portion of this carbon-14 relative to overall carbon in their bodies. Knowing how much carbon-14 to expect, scientists can then measure how much carbon-14 is left in ancient items to figure out how much time has passed since the object was living. Part A. If a living object was supposed to contain 1,000 grams of carbon-14, how much would you expect to remain after one half-life? So if it's been one half-life, you would expect only half of it to remain. Half of 100 would be 50 grams. After two half-lives, so after the first one, we're at 50. Now another half-life goes by, so another 5,730 years. Only half of it should remain again, so from 50 down to 25 grams. Draw a graph showing the expected amount of carbon-14 in half-lives. This is similar to our pennies. I'll quick plot the graph. Question C. Write an equation for the function that represents the amount of carbon-14 that it will have. So we'll start with our y equals, this situation started with 100 grams, and our multiplier, if we only want half to remain, that's a multiplier of 0.50 or 0.5 to the x. And y is counting how many grams of carbon we still have. X is keeping track of the number of half-lives that have gone by. What output does your function give for an x of 0? That's the starting point. We would have 100 grams to start with at 0 half-lives. What output would your function give for an output of -1? Well, that -1 would be going 1 previous to the starting point, and it has to get cut in half. So we would have started at 200, one spot before, so that half of it would get us to 100.